In this video, I show you how to build a production multimodal RAG for medical scans with both explainable and evidence-based retrieval in a full Gradio interface. To reflect real-world complexity, we are using 10,000 real-eye scans to detect multiple diseases. For the tech, BiomedCLIP for medical embedding, Qdrant for vector database, and Gemini Pro for the diagnostic reasoning. I'm Mariam, PhD with 20 plus years in AI, teaching thousands to build AI agents in 90 plus countries. Let's start building. I'm in Google Anti-Gravity IDE, which is basically the same as Cursor or Visual Code. These are all the Python codes that we need to build: preparation, embedding generation, UMAP visualization, vector indexing, explainable evaluation, and finally building a Gradio. Let's first prepare the data. We get our data, which are the left eyes and right eyes of 5,000 patients. Each eye can have different diseases. We treat them separately. As you can see, the data is from Kaggle. So what we got, 5,000 patients. We are making an image from fundus in their eyes, left and right. Real life patients from China. Varied cameras, Canon, Zeiss and Kowa, different resolution as well. They are annotated 8 different diseases: diabetes, glaucoma, hypertension, and so on. Back to code, we simply download that from Kaggle. Data has 2 parts, the text part and the image part. We make sure that we know which patients is the left and the eye, so we flatten it to eye level. We finally have all of the information there, and we put each image in the examples directory. So we have different images that has been downloaded here. And if I run the code, just basically ask it for 10 images for demo purposes, and we get actually these images download. Everything can be added here. In this way, we can batch download actually all of our 10,000 images. And if you click away, we are basically done with this part. So phase 1 is completed. We already have all of the text and the individual images downloaded. Okay, now we can build our embedding with BiomedCLIP. But just before that, we need to know actually what's the goal of building. In this case, we have all of these 10,000 real eye scans from diverse hospitals. We want to put them all in a multimodal RAG. We want them to be searchable. The reason is every time that a new patient comes and we make an eye scan from them, to find the top 3, for example, of eye scans to be found. And because we have all of these labels for each of our images, what kind of diseases they have, now we can use that to give disease probability score and make a diagnostic. But same as for text, we have to change that text to numeric, and then numeric becomes searchable with similarity. The same for our images. So we need an embedding for images. One of the best one and most high quality one is CLIP from OpenAI. And this embedding has these properties: feeding an image to a vision encoder, and then we'll break it into patches and learn the patterns, and it would give an embedding vector. The advantage is that it has been trained on 400 million image and text pairs, so just not labels. It can make that comparison between the text and the images. But this embedding capture is basically objects, visual attributes like colors and texture, spatial relationship, abstract concepts like mood and context, and also text visible in images. The CLIP stands for Contrastive Language Image Pre-training. And in the contrastive learning, we teach a model by showing it what goes together and what doesn't. So for example, if I will have a number of pens and I will have a number of markers and then maybe some permanent markers, they're all writing stuff. But after a while, the model can just distinguish between all of these types. And because it's an image and text pair, the place where image and text are in the embedding space, in embedding vector space, is exactly the same. For example, this image and detects that it's ocular fundus photograph showing signs of diabetic and macular edema will be tackled by our embedding. But one of the problems that we have is that we have images from they are medical images, so they are very difficult to get that pair together. We don't want our embedding model to make mistakes. We need actually an embedding system which is fine-tuned with medical images. To do so, let's head to Hugging Face. So this is BiomedCLIP trained on 15 million figures. This is the embedding model that we are going to use. And in a nutshell, a BiomedCLIP embedding, you can use it via OpenCLIP, which is an open source of the clip. It has been fine-tuned by 15 million biomedical image and text pairs. It understands lots of diseases, and it has a 512 dimension pure visual embedding. And we can use cosinus similarity with L2 normalization. And the source is PubMed data source. Is one of the very famous data in medical world. By the way, I can imagine that building AI agents can be very confusing by the big number of tutorials out there. I made a complete module of my paid course, AI Agent Mastery, for free. It will bring you from 0 to hero in just 30 minutes. It's the first link in the description. And if you're ready to dive into AI agents, I would love to see you in my AI Agents Mastery 5-in-1. The link is also in the description. Heading back to our code, to our embedding, this is where we are going to create that BiomedCLIP embed, and we are going to use OpenCLIP, and of course the path from Hugging Face. So we're going to use image open, image tensor, then doing an embedding with an encoding of that image. We are going to use L2 normalization, which will improve our quality, and we can also do that in a batch format when we have a number of images. We look at our image paths when we do that. Reading the dataset, use an embedder from the type BiomedCLIP embedder, which is this class. Validation, check if the embedding exists. Then we do check the normalization. It should be close to 1 when we use actually normalization. Then we check if there are 0 embeddings. So a bunch of tests to get if the embedding is working, and finally the summary statistics. So let me run this. So I'm testing with 200. First, we downloaded from Hugging Face. That's why you will also need your Hugging Face credential in your environmental. Then it will load and will open via clip. You're going to do eyes with a batch size of 32, embedding, as you can see, 512. And the shape of 200. We are validating it. It should be close to 1. We can see it's close to 1. Saving it. All of that we can save to file. And we also have the metadata, as you remember, all of the text like the diseases. And we save that one as well. By the way, if you're wondering, okay, why you don't summarize these texts and put them in the database instead of the images, in this case, because we are working with the image comparison, we want actually the image themselves. But I have another project, which is for flowers in an auction, about 43 million flowers a day, which we need a speed. So use clip only when your use case, like here, really needs the images itself. So we are going to do a UMAP from our embedding. So our plan for UMAP is that we've got anything before we index it. We project actually all of that to a 2D UMAP. We make those clusters, compute basically the silhouette, the score, and David Baldwin index. Very similar to PCA, a little bit more advanced and for better clusters, and then we can see if the clusters are clear or not. Let me show you what I mean by running the code first. All of these examples that I loaded at the left side, I'm just looking at their diseases and I'm looking at the UMAP. So I want to, this is like kind of same as PCA, to show the clusters of the data. Take a look at the first and second component of the vector. Same we do with UMAP. And we want to see if there are clusters or there are overlap. As you can see, It's a lot of overlap and very difficult to see the clusters. So normal and diabetes are really close to each other. Perhaps this one can be a separate one, and maybe hypertension a little bit here. But in general, you can see that diagnostic is going to be difficult. And also created each of them separately, so we can see what's the distribution of them. So normal everywhere, diabetes everywhere, glaucoma, we've got hypertension. So, and we have even other diseases which can be anything. But this is also to show you how after embedding your images, when you just change their feature to some vector, then you can visualize them and see similarities. Let's go and build our vector database. For our vector database, as I said, we are going to use Qdrant. Mostly I use Phase or ChromaDB, but for images, Qdrant is a very good choice. So our plan for Qdrant vector indexing is that we've got all of this metadata. We're going to put everything in our Qdrant. We're going to use cosinus similarity, and then we're going to use metadata filtering. I'm going to show all of these to you. We're going to create a Qdrant collection. Same as any vector database, you give just the parameters, which is an embedding dimension, because we just pass our embedding. And we say basically that we are going to use cosinus similarity. After that is a bit of coding. We have the data, all of the metadata basically. And I wanted also to convert Qdrant to a clean pandas data frame to do some filtering and see when we put it in our vector database, do we see that the data has been actually stored as we want them. So we are going to do some tests, verifying a test. We are going to ask for a full database, everything. Give us a disease summary to just summarize it. Let's do some stats. We do shape, norm, mean, max, L2 normalized, and then we do some tests. Test 1 is some random query returns. Test 2 is a score valid. Test 3 is a score sorted descending. Test 4 self-match. And test 5 is all the required fields present. Then we're going to do another test, which is age range filter. So we're going to give some filtering. Then we are doing some diabetes filtering and do some combined filtering, so gender and age. And the reason that I do all of this is that just putting it in vector database and hope that everything is right is not a good strategy. You do validation before you pass it to the next phase. And here we're going to print all of the results. So let me run. So all of that is done. You can see that I'm using GPU. Using CUDA or GPU, there's one small trick, just one line of installation that you need to do and speed up actually the whole process. I will show that in a bit, so let me just go ahead and show you the result of this vector database indexing. He has used 200 for demo purposes. Then it's creating the Qdrant collection. Then if there is an existing one, we delete it, we create a new one. We are prepare all of the valid points, and then upload complete. So we have a full database of all of these information for the left eye, what's the age, is a female, and as you can see, that JPEG. So I'm scrolling through the data. Then we had disease summary and counts. So we have normal, diabetes, glaucoma, macular degeneration, hypertension, and pathological myopia, and other diseases. Then we've got vector statistics, shapes, and then we've got information about tests. The test is it passed if you do, I think this was random. Then we got test 6. So this one was a scores invalid, pass, results sorted, self-match of 14 payloads fields, age filter, diabetes, and combined. So this is like all of the tests has been passed, and test 6 is like age filtering. Give me all people between 55 and 65. It should be here, as you can see. It kept the filtering. Diabetes filter. D should be 1 for all of them. As you can see, D is 1 for all of them. Combined filtering, gender female, age 50 to 70, everybody 50 to 70, and female. All of our 8 tests has been passed. At this stage, you could say we can go ahead and build our user interface, but doctors are never gonna accept just, hey, this is your diagnosis. What is the diagnosis based on? What is the support? We are going to do the explainability part. Let's do the explainability. The first thing I do is run explainable for you, and then I will show you the code. So what we have done here is just testing for one specific patient. We've got randomly one of our patients. So it's 10,013, this one. Let me show you. This is actually the image. Then we have retrieved top 10 similar cases to that picture. Then we have created a summary of prediction of all of that. So you say, what is the probability of each of these diseases based on the metadata that each of the pictures have, the 10 that we have found. And then we give an explanation based on 10 similar cases where 40% were classified as other diseases and 40% as diabetes. So basically a complete medical explanation, because we are using medical embedding, is given to the doctor that why actually this diagnosis has been done. And we kind of open the black box. So the code for this, as you can imagine, is we're going to use our Qdrant. We're going to use Gemini to bring all of the reasoning together. We have the disease labels and the colors, which we have used in our UMAP. We have the collection name, we have the query, and we're going to do the search. So we have built actually our multimodal RAG, and now we are searching and querying that. Then we're going to get our results. Add those evidences, the metadata. Then we're going to calculate the probability, which is quite straightforward because we have each of the labels and you're using a weighted summary, calculating confidence, average similarity based on the case similarity. And the case similarity was here, the weight. We can return that confidence, which is a combination of similarity and an agreement, which is disease counts and the values on evidence case. So you can see that's actually that weighted calculation that we had. Then we've got generate explanation. So we're going to explain our data. We are going to do explanation same as you have seen just in the result. The disease code, name, and probability. We are providing actually here, we are using Gemini, giving a prompt, providing 1 to 2, 3 sentences explanation in medical but accessible language. So perhaps also for nurses, it's still understandable. And then we pick up the response from Gemini model, generate content based on our prompt. And after that, it's just predict with evidence. We already have the evidence and we have the answer. So we will give that to our model. Explanation and prediction and the confidence. Then we are going to test our RAG pipeline by generating, as I said, just a random person, the image, and we are going to explain it. So now we can use this explainability to build our user interface. And what we could also do is add those pictures and those images that has been selected. In this way, they can also visually see what has been selected. But just before we get to building our Gradio, is explainability alone for doctors enough to say this is a trustable system? Not really, because they need also an overall evaluation of your system, how good or bad do you think that general prediction is? Same as with machine learning, we said, okay, this is our overall error and this is our local explanation. So we used to do that with sharp values and an overall prediction. We had always precision and recall and F1. So we're going to use those for evaluation. And I'm going to show you also another thing which shows way better evaluation than precision and recall and F1. So best thing is to run evaluation and then showing you the evaluation code. But just before that, I have promised that if you use GPU, you're going to be way faster. This is the line that I had to pip install next to my requirements. Then you can just immediately use GPU. So let me get back to 6, run. As you can see, it's just generating evaluation for all of the data points and give me an answer. So these are all of the evaluations. And what I do is just eye by eye, just check. And because I have the labels, it's very easy to evaluate. So for these, as you can see, probabilities are low. We want to see overall, and I showed you the UMAP, which was showing how difficult it is to diagnose. But we want actually the overall score. So precision, 75%, recall, 100%. F1 score is almost 86%. And I also used a new index, which is called Jaccard. Just let me explain to you why Jaccard. We know F1, we can combine precision and recall and just have this one measurement that do we have a good model or not. But there is another index called Jaccard, which is basically F1 divided by 2 minus F1. And you can see if F1 is about 80%, then Jaccard is about 67%. Well, why Jaccard is better than F1 in our project is that the patients can have multiple diseases, prediction as like sets and not class by class. And we want them actually to penalize for false positive directly. So if RAG retrieves a case with extra labels, those bleed through in the vote. So Jaccard catches actually this way better. If it's 1, it's a perfect match. If it's 0, no overlap at all. So this is like the reason that we use Jaccard, and we trust it a little bit more than F1. And I can see that Jaccard is here for all of the cases about 79%. And we have the also per disease. Looking at this and knowing that this was our UMAP, you can remember this is almost no cluster in there, and there is a lot of overlap. So it makes it very difficult to predict. It shows that still we have done a great job with BiomedCLIP combination with our good retrieval. And then we can see if we do randomly. So we need a baseline. This is our baseline, and with our RAG system, about 79%. It shows that we've got big improvement for our detection and in how far they can trust actually this system. Now we can just go ahead and we can wrap it together in our Gradio user interface. Building Gradios is really straightforward. What you do is you use Gradio. We collect our real images from the dataset. We initialize our RAG system. Then we go and load the ground truths from evaluation mode. We're going to collect real example images from dataset. We write a custom CSS, which is, I say, you want some green and white. What should be the header? How big should be the images? If we are hovering, it's pretty straightforward. Then we get disease color, add color border. We're creating a probability chart. We're going to use that Gradio, show a figure, well, update layout. We are creating now an evidence gallery, generating confidence, then generating explanation of HTML. This is nothing but getting actually our information and just presenting it very well inside that Gradio. Then we are going to get ground truths, which is from our disease colors, the main diagnostic, if RAG system basically pick up something, we are going to use that RAG system and predict it. And everything we create and generate, we are putting it here in our output and use them actually later on. And finally, we're going to build our Gradio interface based on all of the functions. It's always a Gradio block, HTML for just showing the names like explainable ocular disease, ocular for the eyes, and how it works. The system uses BiomedCLIP, so just some explanation, the rows, the column, the image, the slider, a checkbox. We're going to do disease plot, confidence plot, explanation plot, and ground truths. And finally, evidence gallery. I'm going to use a button, which is like diagnostic button, which will use some inputs from all of these and create an output like this. And finally, at the end. So let me run it for you. So when I run it, I get a URL. If I go, just hover on it, you can say follow link. So this is what I build, like the top part and how it works, because then you know that these are some of our data. So we just show example cases. How does it look like? So I'm going to go and pick up an image. Let's go with this one. So I can say 1, 2, 3, or 4, or 10, depends on. Let's go with 4, diagnosis. As you can see, it has been just real matches, very high confidence, this one. Other diseases or pathological myopia. So we've got evidence cases. You can see here our doctor and medical staff can see what's the match. On each of them, we can see the match. So this 100% is 92%, 89%, and 91%. And we also get like, what's the diagnostic? We think that's a pathological myopia. And based on the 4 visual similar cases for our databases, so just fully explanation, we can go and try something completely different. Let's do this one. And let's do a little more going to be problematic, I think, but let me show you if we got 6. And this looks very specific as well. You can see the confidence goes down because it's 100% match. This is 97%, 96, and 96. But then the diseases are not matching that well. So what we could do is just, let's try if we have 2. Just how, this is 71%, so medium confidence. Let's see if we can improve the diagnostic. Yeah, 99%. So you can see that your top end is very important, that you don't create too much of noise. Just in a second, I will explain to you how to do these kind of things with other documents, like complex PDFs. But for now, I think this is a really valuable app for diagnosis of medical imaging. And we can improve each of these pieces that I built. We can even improve, can we improve embedding, can we improve indexing, ranking, all of the steps that we have chosen. But for the difficulty that we have faced, we have actually built a very solid and good system. So let me tell you how to do this for very long, complex PDF documents. So how about the time that you want actually to parse your documents and there are these complex, lots of pages with text and tables and images? You can use all of these tools. I've built this and tested the newest Andrew Ng DPT2 Docklink Llama Index in this video, where I explain how to parse them, but also how to use RAG for evaluation. So I see you in that video.